Okay, so today we talked about strain, this idea of a quantity that we use to measure and describe the intensity of deformation. Deformation in this case is our change in dimension of our element. So we looked at this little square, we put a force on it. That force imposes stress, that stress imposes deformations. And we use the dimension of strain in order to quantify that level of deformation. So there's a couple different types of strain depending on the stress imposed. So as you can imagine, we've got normal stress and we have shear stress. Well, we have normal strain and shear strain. Normal strain is a change in member length or width that results from the normal stress. And with shear strain, we have what we would get, we call angular distortion from our shears. So as we looked today in class, we had our normal stress and shear stress, positive and negative sign conventions. And as we impose those stresses on an element, for normal stress, right, compression or tension, shear stress, a positive or negative shear, we impose deformations in that element, as we can see here. So we started with normal strain. That's 2.2 in the text. We have this term epsilon, right? This variable epsilon that we make up, and that is essentially strain or our normal strain. And we define normal strain as change in length delta, as you can see in the depiction here, over the original length. And as I mentioned, important to note that this is the original length and not the overall length or the changed length. And so if we look at a positive shear or positive normal stress, right, positive sigma n, we have tension, and that tension results in elongation of our element, and that would be denoted as a positive strain. Conversely, if we looked at negative sigma n or normal stress, we have compression, resulting in shortening, and this gives us a negative strain. As I mentioned above, if we look at the equation for strain, epsilon being delta over L, both of those have the same units. They're both dimensions of length. So it's inches over inch, inches over inch, meters over meter. Often, strain is quantified is a very small number. So we end up using oftentimes micrometers over meters or micro inches over inches, where, if you guys haven't remembered, micro is 1 times 10 to the negative 6, or essentially dividing our number by 1,000,000. Sometimes it's also referenced as percents. As a percentage. So if we had an epsilon or a strain equal to 0.2%, well, that is the same as saying 0.002 inches per inch or meters per meter. Right? And when we classify something or call something out as having a strain, right, that being a unitless number, right, it can cross over between units, right? 0.002 inches per inch is the same as 0.002 meters per meter. So we're going to go through an example. All right, in our example, we have 2 rods. As you can see, they're different diameters and lengths. So when an axial load is applied to the ends of the 2-segment rod, okay, shown there, the total elongation between joints A and C, right, those are the ultimate ends of our 2 rods, is 7.5 millimeters. The segment lengths for each of our rods, right, segment A is 1.2 meters and segment B is 2.8 meters. In segment 2, the normal strain is measured as 2,075 micrometers per meter. And they want us to determine, right? So this was given. They want us to find, right, our normal homework problem statement setup, find the elongation of segment 2 and the normal strain in segment 1 of the rod. So if we start with our solution, right, homework setup, and we're looking at A, right, the elongation of segment 2. Well, we're talking about strain, and if we start with our known equation, which we can all find in our appendix that I posted to D2L or in the text, right, appendix E, I believe it is, which is our list of equations. Right, when we're talking about strain or epsilon, it's delta over L, right? And so we really want to know what the elongation of segment 2 is. Well, the elongation is our delta. So we can rewrite this equation. We can say, okay, delta 2 is what we're looking for. We're going to rearrange this equation for epsilon 2, the length of 2, right? The original length of 2. Well, they gave us the normal strain in segment 2 in our problem statement was 2,075 micrometers per meter. So if we take a micro as 1 times 10 to the negative 6th, and we start out with 2,075 micrometers per meter, well, that really equates to, if we divided by or multiplied by 1 times 10 to the negative 6th, we could get 0.002075 meters per meter. So if we go back to our equation we just developed, right, our delta 2 or our elongation of 2 is really the epsilon of 2 or the strain of 2, which we just have, they gave us in our problem statement. Meters per meter. And we have in our original length of 2, they gave us as 2.8 meters, right? Watching our units here, right? We have meters and we have meters. Well, that boils down to a change in length of 2 of 5.81 times 10 to the negative 3 meters, or knowing that 1,000 millimeters per meter, right? So if we multiplied this by 1,000 millimeters per meter, we would get 5.81 millimeters. And that would be our elongation of segment 2. So we don't know what the load was on this, but we did measure the strain. And based on knowing the strain and the original length, we can figure out how much that bar stretched under that given load. So 5.81 meters or millimeters. If we look at part B, now they want us to determine the normal strain in segment 1 of the rod, right? Normal strain we know is epsilon is delta 1 over L1, right? Well, we were given in the problem statement, right? We weren't given the elongation of segment 1. We were given the length. So we don't know the elongation of segment 1, and we don't know what our epsilon or our strain is in segment 1. But what they did give us was the total elongation between points A and C, right, in the problem statement. So we can say that our total elongation is delta 1 plus delta 2, right? So it'd be the total change in length of our system, which is comprised of our 2 rods. So that essentially means that 7.5 millimeters minus 5.81 millimeters equals delta 2. Is delta 1. Right? If the total is 7.5, we take away from that the elongation that we calculated of segment 2. That's going to give us the elongation of segment 1. What does that mean? That means that segment 1 is 1.69 millimeters. Well, now we have delta 1, so we can just plug through the equation. Epsilon 1 equals 1.69 millimeters divided by 1.2 meters, right? That was the length of A. Well, before we get ahead of ourselves, right, we need to have consistent units. So what do? We multiply by 1 meter over 1,000 millimeters, right? I converted to millimeters. You could have kept it as meters. Or sorry, I converted to meters. You could have kept it as millimeters if you wanted to. Right? So in this case, our millimeters essentially drop out. We get 1.408 times 10 to the negative third meters over meters. Or if you wanted to keep it in millimeters, it'd be 1.408. Oops, no times. Millimeters per millimeter. So we looked at this drawing, right? If we had these two rods, and say you fixed one as a reference plane, right? One end as a reference plane, and assume that it doesn't move, right? It's still going to impose a force P, and we have another force P, right? Whatever force we put on this, we're saying that overall we have 4 meters in length originally. Whoops. And in the end, our initial segment 1 elongated 1.69 millimeters. And our segment 2, delta 2, is 5.81 millimeters. All right, so under that given load, segment 1 deflected less than segment 2. And as we're discussing, we'll talk further about Poisson's ratio, right? As we elongated these rods, those rods would then effectively get smaller in the transverse direction. All right, we're going to go through another example. Okay, given the setup we have here, we want to determine the strain in rod 1 if the strain in rod 2 is negative 0.003 meters per meter. Well, let's get rid of meters per meter first. That was a mistake. We're going to call this feet per feet. Right, essentially the same thing, but we want consistent units with the diagram. As you can see there, all of our dimensions are in feet. This would be the same as saying negative 3,000 microfeet per feet, right? Essentially multiplying by 1,000,000, or 10 times, or 1 times 10 to the 6th. So as we look at this, right, determine the strain in rod 1 if the strain in rod 2, okay? We're going to have to make an assumption here. I'm going to make an assumption. I'm going to say that this rod is infinitely stiff. What does that mean? Well, that means that as this bar moves, right, it moves as a rigid body. There's not going to be any bending going on, right? This isn't going to do something like this. Okay, that's not going to happen because it's infinitely stiff. It's going to stay as a straight line bar. So if we look at a deflected shape diagram of what's going on, right, essentially a free body diagram, assuming that we have some displacements, and we say we start out with this bar as we've seen above, okay, and we have bar 1 holding on, right, and we have bar 2 holding on, okay, we have a pin connection at the end, we saw in the diagram. So what does that mean? That bar is not going to be able to displace vertically at the end. So if there is a strain in rod 2, right, that was given in the problem statement as 0.003 feet per feet, okay, negative 0.003, that means compression, right? It's due to a negative stress or normal stress. So that's going to get shorter. If it gets shorter, that means that this bar is going to rotate downward, right, about this pivot point. So if we look at this rod now, it's going to do something like this. Right, that'll be our deflected rod. Rod 2, and we have rod 1. We throw some dimensions here. Right, we have 2 deformations that are due to the rotation. We have a negative strain in rod 2, right? That rod is getting shorter. Well, if we're fixed at this pivot, right, this pin at the end of the infinitely stiffed beam, okay, and rod 2 is getting shorter, so it's rotating downward. If it rotates downward, then rod 1 is going to have to get longer. Those changes in lengths are delta 1 for rod 1 and delta 2 for rod 2. We're ultimately trying to determine the strain in rod 1, right? Knowing the strain in rod 2. Well, if we start with our known equation for normal strain, right? It's delta over L. We can start looking at similar triangles. Right? If we boil down our little diagram here, even simpler terms. If we had a triangle and at rod 2, we have delta 2, right? And because this beam is infinitely stiff, as it rotated downward, we're going to have 2 straight lines, right? We have a straight line here and straight line here. It's essentially the same fixed rod. As it rotates downward, we're going to have delta 1, right? We know some dimensions from up above. We have 5 feet. We have 5 feet. Well, if we look at similar triangles, right? Similar triangles will tell us that delta 1 or delta 2 is 2 times delta 1, right? It's twice as far away from our pivot point right here, right? So if we've got 5 feet to delta 1 and 10 feet to delta 2, for every 1 motion at 1, we're going to get 2 of those motions at 2. So delta 2 is twice delta 1, or delta 1 is 1/2 delta 2. Well, if we rearrange this equation for strain, right, we don't know what delta 2 is. but we do know the length and we do know the strain, right? They gave that to us. So we could say delta 2 equals epsilon 2 times L2. What does that mean? Well, that means that we had a negative 0.003 feet per feet times 2.5 feet. That's our length, right? That's our length of rod 2. What does that give us? Well, that's 0.0075 feet is delta 2. Well, we want to determine the strain in rod 1 while using similar triangles, right? Because our infinitely stiff beam is going to create straight lines as it deflects. So the proportion of deformation at 1, or 1 is in proportion to the deformation at 2 and vice versa. So we know that delta 1 equals 1/2 delta 2, or 1/2 0.0075 feet. Or we have epsilon 1 equals 0.00375 feet. So that's our strain in rod 1. Or sorry, that's our delta in rod 1. I'm getting lost here, not having all you guys keep track of me. Right, sorry. Delta 1 as shown above. Right, it's moved 0.00375 feet. Well, we know epsilon 1 is delta 1 over L1. Well, we have both of those now, right? We have delta 1, just calculated it. L1, given up above, it's 4 feet. So we have 0.00375 feet divided by L, which is 4 feet, right? That's this guy up here. So we get a strain in 1 of 0.000938 feet per foot, or 938 micro strain, right? Sometimes denoted as just strain because inches per inch, meters per meter, it's unitless. So regardless of what units you attach to the end of it, it's essentially just strain. Microstrain tells us that it's 1 times 10 to the negative 6th, right? So 0.000938 instead of 938. But sometimes it's easier to do full numbers, such as that. So that would be our answer to example 2. And that's really normal strain. As we were saying, there's deformation attached to normal stress. Well, there's deformation attached to shear stress. That strain is called shear strain, or that deformation is called shear strain. This is 2.3 in the text. Okay. Shear strain is denoted as our gamma. Whoops, terrible gamma. That's our shear strain. All right, this is a positive orientation for shear strain, right? Up and to the right, it's going to put us into this rhombus that we see here. Okay. We started out with an original shape, right? That would be this square here. And our shear strain elongated it. So if we look at this, underneath a positive shear stress, right, the blue arrows, as it morphs into a rhombus, right, it's going to undergo some rotation, as you can see with theta, right, we have theta. Well, because of that rotation, our upper corner here will rotate, right, or move to the right a distance delta, call this delta x. And our exterior angle, or essentially the rotation from vertical that our leftmost face underwent, is this idea of gamma, and that is what our shear strain is. And our shear strain is tangent of our change in length over total length, right? And in this case, though, our delta x is not the change in length of that side, but the distance in which that side rotated, right? So the distance of this triangle over the length it was of that side that rotated. As you can see from the equation, right, the tangent, opposite over adjacent, right, delta over L in this case, right, this would be opposite over adjacent. That'll give us this angle, which is gamma. Right. So tangent of delta over length, well, it's unitless, right? The tangent of that number, though, gives us units of radians. And you had this in math class. Radians equals degrees over 180 times pi. Right, so there are pi radians in 180 degrees. There are 2 pi radians in 360 degrees. So you can take your degrees and multiply them by pi over 180, and you will have your angle in radians. You can take your radians and multiply by 180 divided by pi, and you'll get your angle in degrees. So pi radians equals 180 degrees. As I mentioned, this is our resultant force on our cube, right? That initial red cube is up and to the right, our positive shear strain. So what is our sign convention here? Well, if we had theta 1 being our original angle, right? Our inside angle of our square, as we can see here. So if theta 1 is greater than theta 2, our shear strain is positive. If theta 1 is less than theta 2, our shear strain is negative. Kind of makes sense, right? Theta 1 is greater than theta 2. That essentially means the angle gets smaller at the corner there. What does that do here? Well, if you looked at our box, I'm going to draw it in black so it makes more sense. All right, so if we had x, we had y. If theta 2 is less than theta 1, we're going to get something like this, right? Where that theta 2 gets smaller. Well, that means we have a positive shear stress, right? Up and to the right, it's elongating. Well, that also means that we have a positive shear strain. Conversely, if we look at negative shear strain, we do something like this. Right, and we have down and to the right. we have a negative shear stress. Similarly, we have a negative shear strain. All right, this being theta 2. So we have theta 1 turning into theta 2 based on the imposed stresses. So what is this small angle approximation all about? Okay. Well, as we saw with our normal strain, with shear strain, we're talking about very small amounts of deformations. So our delta that we saw up above, right, the highlighted delta up there, right, when delta x is a lot smaller than our adjacent side length L. When I say it's much smaller, I say L is at least 10 times greater. So if we were looking at a block, right? Say this block was 1 inch cubed, right? So L was 1 inch, right? Delta would have to be at a maximum 0.1 inches, right? Which is pretty significant. If you looked at a 1 inch by 1 inch square, right? And you sheared it, you put the shear stresses on it that we're depicting here, okay? In order to meet the small angle approximation, right? Delta, or the distance that that upper left corner traveled, would have to be less than 0.1 inches. So pretty consistent, something that's not that hard to accomplish. We essentially get delta x over L is a small number. If that's a small number, the tangent of delta x over L is approximately equal to delta x over L. Well, if that's the case, based on our definition of shear strain with gamma, we now say that gamma is essentially delta x over L. Hopefully this is all making sense. Try and find my notes here. Okay. Trying to see here. They tell me we also have gamma equals pi over 2 minus theta 2, right? This being theta 2. Essentially saying 90 degrees minus is, oh, that's because we have complementary angles, right? We know that if we look up here, right? Oops, this is gamma, right? This is gamma. So really gamma is 90 minus theta 2. So as you can see in our negative sense, right, because theta 2 is greater than 90, we're going to have a negative number, right, because 90 degrees equals pi over 2. So this is just stating that we have complementary angles. So if we know what that angle is, our shear strain is 90 minus that. So these are our big equations to pull out of shear strain. Not a super straightforward dimensional property, but obviously very important to know. Okay, let's do an example. Hopefully this will make things come together a little bit for everyone. All right, we have a thin triangular plate, right, denoted by PQR, and it forms a right angle at Q, right, so we got 90 degrees. During deformation, right, don't give us loads or anything, but just saying that based on imposed loads on this triangle, right, the triangle deforms. And what they're saying is point P and point R are fixed, and point Q moves to Q prime, right? So really what's this saying is we have a triangular plate. Maybe it's some sort of stiffener plate on the side of something, and we had some load, right? Some load P acting at Q, and it was acting kind of up and to the right. And based on that loading, it moved that point Q, right? Deformed this plate so that it took on the deformed shape of Q prime. So maybe there's obviously a real world application. So point Q moves up and to the right, U of 0.8 millimeters, right? So that's our kind of our X coordinate, if you will, and upward by V equal to 1.3 millimeters, or Y coordinate, to a new position Q prime as shown in the figure. So determine the shear strain. So now we have our find, right? This is our given. We have our find. And it says determine the shear strain gamma at corner Q prime after deformation. Well, if we're looking at the corner at Q, right, that's essentially saying that our corner Q is our corner at A, right? So we're interested in what that angle is doing at Q, right? We know at the beginning here, it says that we have a right triangle. So this is saying that theta 1 is 90 degrees, or pi over 2, right? So theta 1 is pi over 2. We know that V equals 1.3 millimeters. We know U equals, it equals 0.8 millimeters. So we pull out this right triangle, right? And we have this deformed shape, right? We have theta 1 is pi over 2, it's a right angle. And then we're interested in what theta 2 is. Right? What's our final angle? Our final angle when we have our Q1. Well, we know from above, because we have complementary angles, we can say that pi over 2 minus theta 1 or theta 2, get that right, theta 2 is gamma, or our shear strain. Well, let's start by, essentially, I'm going to be pulling out our deformed triangle. So if we look at our deformed triangle, try and copy what's essentially up above. If we have our deformed triangle, maybe it looks something like this, right? It would look something like this. This is Q1. In order to simplify geometry and understand some of these lengths, some of the angles, I'm going to kind of break this triangle down into two triangles. I'm going to give one angle on the right-hand side as beta. The other one on the left-hand side is alpha. Okay. If we want to know what the height of this triangle is, right? Now we have essentially two right triangles. The height of this triangle, if we go back, we've got D, right? And we have V. That's essentially the height of the triangle, where we are given D as 319.96. Okay. 319.96. Well, if we add 1.3 to that, we're going to get 321.26 millimeters. We also want to know what the distance to the center is, right? Well, they gave us A as 225 millimeters, and they gave us B as 455 millimeters. And they also gave us U. Well, when we displaced over to point Q prime, I don't know why I called it Q1. Well, at Q prime, right, we displaced over U, which is 0.8 millimeters. So 225.8 millimeters is our distance to center of Q prime. 454.2 millimeters is our distance from Q prime to point R. Well, we know that our two angles, right, from up above, we have theta 2 divided into two pieces, right? So we have alpha plus beta is theta 2. We know from trig that the tangent of alpha equals opposite over adjacent. Well, we have those two dimensions, right? We just determined what those were. Well, inverse tangent will give us alpha, right? Tangent -1 of opposite over adjacent. So we can say the tangent, inverse tangent, 225.8 divided by 321.26. Well, that gives us alpha. We're going to get alpha in radians, 0.6126 radians. And you're only going to get alpha in radians if your calculator is set to radians. So make sure you go in your calculator and make sure it's set to radians. Otherwise, when you do trigonomic functions or sine, cosine, and tangents, it's assuming your input is in degrees. Well, we need to be in radians. So make sure you're in radians. So we get alpha as 0.6126 radians. Well, if we do the exact same thing with beta, right, it's going to be the inverse tangent of opposite over adjacent. In our case, opposite is 454.2. Adjacent is the same as alpha. So beta now is 0.9552 radians. Well, we told ourselves up above that theta 2 equals alpha plus beta. Well, that means 0.6126 plus 0.9552. Well, we get total radians for theta 2 equal to 1.5678 radians. Stay with me here. Or rads. Well, we know from up above that gamma, or our shear strain, is pi over 2 minus theta 2. Well, that equals pi over 2 minus 1.5678 radians, or gamma equals 0.002976 radians, or we can do micro 29, just round to 80 micro radians. Is the shear strain at Q, right? So essentially, shear strain is a change in angle, right, at a given location. So our case is the corner Q. All right. So that is strain. We are going to start into mechanical properties. We are going to start into mechanical properties. I'll pull up my notes here. I think this is one of my my favorite chapters. Just understanding more about the materials, kind of the properties that they exhibit, and ultimately that's where we're headed in this class, is to relate kind of materials to internal forces. And so in chapter 3 of the text, it's all about mechanical properties of materials, right? So we have material properties. What are those all about? Well, in a nutshell, it is to determine, why do we care about material properties? Well, it's to determine how a material deforms and fails. Right? This is important. Without knowing material properties, we'd have no sense of the ability for materials to perform well in their application, deform well, have enough strength, have enough stiffness, all of those things. So material properties are really, really important in the grand scheme of design. Right? Some of the big vocabulary terms as part of mechanical properties, right, or properties, is strength. This is a general term for capacity to resist load, right? Strength, how strong is it? Stress, we've talked about this, right? Intensity of a force, right? We have shear stress, we have normal stress, right? We could have a combination of the two. Strain, well, it's intensity of deformation. Again, we have normal strain, we have shear strain. Again, we could have both, right? A combination of them on a given plane or face that might not be acting strictly parallel or normal to our shear stress or our normal stress. Okay, so we have strain and intensity of deformation. Ductility, ability to be permanently stretched under a tensile load. Ductility, right? If you put like a steel bar into a testing machine, you started pulling on it, so the ability for that bar to be permanently stretched under a tensile load, that's its ductility. Malleable, it's your ability to deform under pressure. Hardness, ability to withstand indentation. Toughness, ability to contain, essentially saying absorb energy. Toughness is what we would call our area under stress strain curve. Which we'll go through here shortly. Isotropic, same properties in all directions. Right? Fiberglass is usually anisotropic, right? Which would be different material properties. In different directions. Right, another one would be wood. Wood's anisotropic, right? You have wood grains, so you're stronger parallel to grains than you are perpendicular to grains. Isotropic, right? Steel would be a good example of isotropic. Most steels, generally it has the same properties in all directions. Right? It's milled. It's a consistent material. I would say to end our discussion here, I would say check out this YouTube video. It goes through a lot of different properties and kind of gives you some examples of some. It's super neat. So I will see everyone on Wednesday. Have a safe and fun Labor Day. Enjoy.